And there's all the people. I accidentally clicked on the link for the master's class, and I'm like, where is everybody?
Busy working on their papers.
Oh, you still got 24 hours?
Mine's turned in. I'm done. I washed my hands of it Thursday or Friday. I was like, I'm out. I'm done.
It's always a good feeling. All right. I'm
It is.
sure that Lee is supposed to be coming, but it is also 8 o'clock. Let me just see if that was a message. Okay. She is trying to get on. So let me just ask her if she she's the big draw, I know, but so we'll just see. Not sure. It is recording.
This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make him known.
All right, I have not heard from Lee. It started by itself. So
hey, I'm on, Kirsty. Can you hear me?
I can.
I'm on my phone. My stupid laptop is rebooting something weird. Anyway, everybody, welcome. It's March 20th, 2023. This is where Kirsty and I and all of you very brave people get together and talk about math. So Kirsty, I'm going to continue to try to get on by my laptop. This is difficult on my phone, but can you start the show?
I can. I'll take it over and you jump in whenever you're able.
Okay.
All right. Well, welcome everybody. It is exciting to have you here for another math conversation. And let's see, the PowerPoint will advance for me. There we go. And so this week we are talking about curved lines, and I thought this week that I would choose our reflection as our exordium. And early on in the process, Lee really emphasized the importance of starting our studies with prayer and having some sort of a scholar's prayer. And so we've looked at a lot of different things, and over the course of time, it's become sort of more of a reflection. Not everything that is in this spot on the page is a prayer, but this one is. And I thought that it would be an opportunity for us just to stop and remember that all that we're doing, we want to do for the glory of God, right? And that we put the effort in, and then, you know, he's the one that's going to bring the harvest. And so I'm going to go ahead and read this, and then if you guys want to chat about it, we can. So, Father of light and wisdom, thank you for giving me a mind that can know and a heart that can love. Help me to keep learning every day of my life, no matter what the subject may be. Let me be convinced that all knowledge leads to you, and let me know how to find you and love you in all the things that you have made. What are some things that says to you, especially as an adult, on a math call?
I think one of the things that stands out to me is help me to keep learning every day of my life, no matter what the subject may be, because that takes humility to acknowledge that we don't know everything. And sometimes, you know, we always want to have answers for our kids and when they ask us questions and things. And one thing that I've learned in the many, many years of homeschooling has been that it's okay to just not know and to dive in together. But for me, specifically in math, I almost always don't know. And so it's, you know, that to me stands out as just being humble and being able to say, I don't know it, and somebody else does. And it might even be my kids that know it better than I do. I'm being able to listen and learn from other people.
That's great.
I love that, what Jennifer just said. And I love that it's a great thing to say with our children, knowing that I do have a mind that can know. That is a beautiful gift from God, that he did give us a mind that can know. Not that we have to just hope that we could ever figure it out. And I think it's beautiful that it's tied in with the heart that can love, because sometimes those two things don't seem to go together. We can love something and not know it, or we can know it and not love it. And knowing that we can know and love, those are just really, they're beautiful gifts. And it reflects back to being made in the image of God, that being able to know and love are strong things. And a submissive attitude, like Jennifer was saying, that humility to keep learning, and even a desire to keep learning, because that would, if what it says here is true, that all knowledge helps us to know him more, then why wouldn't we want to learn more? Why wouldn't we want to know God, who is trying to reveal himself to us? I think it models that well for our children when we do that for ourselves. And then this would be a great prayer to keep handy, or reflection to keep handy, if we need to encourage them. And we can say, here, look, this is encouraging to me. Let's say this together.
I love that it says, help me to keep learning every day of my life. I think we all go through seasons where the learning is harder, those newborn days. You're learning the new baby, though, and then also just let me be convinced that all knowledge leads to you. Don't forget that everything that I do learn leads back to him, the creator of everything. I think that's just one of those full circle things. We talk grammar, dialectic, rhetoric, but if we look at one of the diagrams that Cece has, there's a fourth piece there. It's the doxology. And it's like, I learn it, I wrestle with it, I know I have the wisdom, I praise God for it, and then I start over again. And I think we skip that God.
What I like about it is it says, let me know how to find you.
Love you.
I feel like it's this almost this perfect little prayer, right? That in its simplicity, right? There's no fancy words. It's a very simple prayer, but it hits all the bases. And Jennifer, I was just going to say, it's easy for us, I think, as homeschooling moms to sometimes think, I need to teach my children math, or I need to teach my children how to write. But what a gift for you to teach them that it's okay to not have the answers and to go look. That the character that we're teaching our children is perhaps more important sometimes than the academics, because if we teach them to love learning, right? If we teach them to be humble learners, then they will continue learning. And we don't have to fit it all in the 12 or 13 or 18 years that they have with us. So, well, now we're all encouraged. We're all encouraged because we're all going, yes, we can do this. We can get all of this in. So, all right, and it disappeared. My little, there we go. Nope. There we go. I just had to click on the screen. All right, so we are in week 11, curved lines, which is in 2D. And so I just pulled out here as we talk about the map itself, right? That we're trying to use patterns in our titles. So Lee has been really specific. We've wrestled over the titles. They're not happenstance titles, that we really have tried to be very clear what the titles are, that the titles give you a clear picture of what we're talking about in the lesson, but also that by just looking at the titles, you get sort of a feeling of the flow, right? So 2 weeks ago, we talked about straight lines. Then last week we looked at how those lines could intersect. And now this week we're looking at curved lines, right? So we're just building on this layered knowledge about lines. And there we are, week 11, curved lines. And Lee, just stop me if I need to stop. So what I pulled up for us this week was looking at this idea of functions. And so you can see on the left-hand side there in the background is one of our charts, the first chart for week 11. And I've pulled out here just 3 functions. And in the math map, we've whittled it down and we've said, is it 16 functions? 16 functions that we've said, these are the basic functions that if your student understands these functions well, they can use these functions to build any other function in the world. And they're going to be really well prepared for any math that they want to pursue. So instead of looking at, 2,700 different functions, we keep coming back to these same functions and saying, let's really understand these well. So one of the types of functions that we look at are power functions. And I'm not going to get too in detail here, although I could, because I think this is really exciting. But if you look, they're all of this form, like this would be x to the 0, x to the first, x squared, x cubed, right? So it's x to some power of x, and that's why they're called power functions. And so we're going to look at one of those tonight, x squared, and we're going to look specifically at how we can understand this function in symbols, in numbers, and in images.
Kirsty, can we stop first and look at the chart and make sure we all understand it? I would start from the bottom and go up because it's a little bit simpler. So does everyone see there's a 3 at the bottom box? And then it's the same problem up above, but a 2 and a 1. So guess what the first one's going to be? 0. Having your children learn to read these and look for the pattern in the actual equations will help them to do better at math because it'll help them to see that unseen. The other thing, I want to reiterate what Kirsty said about there being 16 of them. I know I left engineering not even knowing there was only 16 that were foundational to everything else, because all I had seen them was out of order and random and as problems to challenge me. Versus, this is why it's called the math map, is we're trying to help a parent or an interested student say, you know what, I'm not going to know everything about everything. Just like that verse we just read said about, it's going to take us a lifetime. Lord, help me forever. But we should have our children be able to leave 12th grade and say, but I can tell you what I actually do know, because grammar is something that's accessible to anybody. So any comments? Can you follow it? Are you lost before we go on?
Well, it is a little overwhelming looking to me, but we've learned in Essentials doing National Number Knockout that x to the 0 actually equals 1. And you just said that first box there on the right, y equals 0. Like, I think you said x to the 0, which then I do see on the left, constant degree equals 1. Can you just say a little, that pattern, like on the left, we see 1, 1, 2, 3. And then on the right, we see y equals, it's not exactly the same. Is that too complicated to explain?
You explain it, Kirsty.
Sure. So it seems, so one of the things that's going on here, let me just move my pieces so I can see my screen. And so one of the things that we see is this 1 that's showing up here and looks like it's the same thing, because we want to come over here and see this pattern that it's 2 and 2 and 3 and 3, right? We want to see that pattern. And then we come up here and we go, but there's a 1 and there's a 0. And that's because it doesn't just have to be the x that variable, it can be the y variable. So if my So notice it's the highest one, right? So this is really, my screen must be a little bit out of alignment tonight. This is really y to the first power of y. But when I've got 3 and 2, that sort of trumps it, right? Because we go with the highest degree of any term. Here in this one, they're the same. So it's still 1, but once I come up here, my x term has a degree of 0. So now I have to look at my y term, which has a degree of 1, which is why it's 1. Is that enough of an explanation?
Yes, that's enough. More later.
Yeah, well, the thing that's throwing me, Kirsty, is if you have ax minus h to the 0, that should all be 1 plus k.
Mm-hmm.
And k could be 0. So that's y equals 1. And yet we're drawing a line that's right on the x-axis where y equals 0. So it would have almost been simpler to understand if we'd written x to the 0 equals 1 and drawn that red line bumped up a little bit.
Yeah, and that may be something that we want to take a look at, is saying that this is really y equals 1 times x to the 0.
Which is 1 instead of the 0.
Yeah.
So what happened is we confuse things. So this is why we do this. We keep learning, and errors as well as inconsistencies help us. So we were looking at, I'm sure I did this. I looked at the line and it was right on that x-axis. So that's y equals 0. I didn't look at the math that was right beneath it. So even those of us that love math and are always looking for these patterns, we're still going to make mistakes. There's so much to see. And this is why I think math needs to be more of a social subject. We need to say the things out loud and ask people questions, because then we catch these kind of inconsistencies. So
no,
what? Go ahead.
I was going to say, because and maybe I'm misunderstanding, but it says constant degree, but k is to the 1, right?
Well, no, it's
or no.
Those are two. It's constant is the name. Let me just erase this over here so you can see it. So constant is this is the name of the function, is the constant function, and its degree is 1.
Oh,
right?
okay. So it's not the degree of the constant.
Right.
But Kirsty, that's really good though too. We probably should put a little bit of space between there.
Mm-hmm.
Yeah. Thank you.
Does that help, Carrie?
Yeah, sort of. Like, yeah, I'm like, yeah, it's a little overwhelming.
Let me just say that we're gonna pick out just some concepts from this week. This is one of the more challenging weeks in the math map, because we're going to talk about, there's a lot of notation. There's a lot of algebraic notation. It looks overwhelming if we don't slow down and really look through it. And so eventually when you're using the math map curriculum, you're going to be like, oh, here's that week 11. One of the things I really like, that I've learned from Lee over the years, is that she's always like, we need to have times of rest. And so there'll be a hard week and she'll be like, no, we can't have 2 hard weeks back to back. There's a hard week. And then the next week she'll be like, they need a rest. They need something familiar, right? They need something that's accessible. So we're going to look at angles. Last week, most of the lesson is angles. So it feels more restful. And then we've got all this function stuff that's going to feel challenging and unfamiliar. And if you remember Algebra 2 in high school and it was hard, this is going to bring back some of those memories. And then you're going to go next week, we're going to talk about polygons, and it's going to feel more familiar again, right? So there's a pattern throughout the math map of it doesn't build, right? This is not a curriculum that builds and it's like, oh, I got to this thing and I don't understand it, I can't keep going. That's not true. We're going to see these ideas again, but interspersed with other things that are really accessible. So I just want to encourage you that if you're looking at this going, I can't do this, that's it, I'm done. Well, come back for next week, because you're going to feel a lot differently. And hopefully after tonight, when we just talk about a little bit of what we cover this week, hopefully you're going to go, oh, well, that wasn't so bad, right? Again, it's a lot of notation. Don't get too hung up on the notation, because nobody becomes fluent overnight, and we're not going to become fluent in 15 minutes of a book club Zoom.
Yeah.
Right.
You know, Kirsty, let's do something a little simpler than what you were going to do for just a moment. So let's take the words that you circled and look at the actual graph. Can you see that the red line in the first graph has it, that it is a constant, that it's like level, it's not really doing anything, but it's still a line, isn't it? But then the next one, we called it the line. Well, that's because it's not a constant. It could have a slope that changes on you. So then you look at that, you see a quadratic, and we have in parentheses that that's a vertical parabola. Everyone wants to know, why is it called a quadratic? I can understand why it's a parabola. Turn it upside down and it looks like a parasol. Right? So we got to find these mnemonics, these ways to remember things. And then the cubic is always that. You should see Kirsty do that John Travolta dance whenever she talks about cubic equations in our math map development. So helping your children just have fun with the information to the best of your ability. I know that it's not naturally fun, but I bet you can make it fun by helping them just come up with crazy ways to remember things.
And just so that I'm understanding that is it called the vertex? It's not always going to pass through the origin, right?
No.
Okay.
So we probably need to fit in. We have the space, Kirsty, to say vertical parabola there.
I'll try. There's other equations that are longer.
No, but okay.
I would say, Carrie, one of the things that your point, what you're saying there is, if you look, we say there's a parent and a general equation. So parent functions, take out the constant one, because however we talk about that one's a little bit differently. But as long as the X, right, that those other ones there, generally speaking, parent functions are always centered at the origin. Right. So my line is going to go through the origin. My quadratic is going to sit on the origin. My cubic is going to do its curvy bit at the origin. And we're going to see that the origin, that they're all centered on the origin. That general equation where you see that H and K, if those numbers were not zero, then I could take that image, that graph, and move it anywhere in the plane. Right. And so,
okay.
One of the things that we've talked about is looking at both of them, but usually what we're presenting, especially to the younger students, is that parent graph, just becoming familiar with a shape, right? So it doesn't matter where in the plane my parabola is, it is always going to look like a bowl. If it's positive, or if it was negative, then it would look like the parasol, right? That it's always going to look like that if it's an X squared. And my cubic is always going to look opposite, right? It's always going to be opposite. So those are the things that we're hoping students can learn early on and become just really familiar with that, so that they could see it anywhere in the plane, and they could see it narrower or fatter, and they're going to go, oh, well, it's this kind of an equation, right? So, all right. Oh, can I move on, Lee?
Sure.
All right. I'm going to clear that just so you guys can see that. And let's come over here, and there's a couple of things that I wanted to just address. First, when we talk about a function, right? Notice here I've written in symbols y equals some function of x equals x squared. And sometimes we talk about it as either a rule or we talk about it as a map. And what we're saying is that I have two sets. I have my set that's my x, and I'm just going to write, there's my x, and I have my set that's my y values that are going up and down. Right. So I have two sets of numbers, and my function says, how do I match a number in my X to a number in my Y? Right. If you haven't been on CC Connected and seen the Math Map materials there, I did a little video using my daughter's dolls to describe this idea of a function being a map, which I thought was helpful. So I created it. I may be wrong, but if you're sitting here going, okay, well, how does this whole mapping thing work? You may want to go on CC Connected, look in week 11 and watch that video. And it'll kind of give you a visual of what we mean when we say we're mapping from one set to another. When I talk about the function, right, I'm talking about where those X and Y points all stack together. Right. And so my Y value is some function of X. It says that my Y value depends on the value of X. So in symbols, when I say Y equals f of X equals X squared, I say that the value of Y, any X value, right, is going to be that X value squared. And so just in symbols, what's something you know, when I square something, what do I always end up with?
A positive.
A positive. So just in symbols, without even looking at the images yet or the numbers, if I know, right, whatever X value I put in, what kind of a Y value am I going to get? A positive, right? So in symbols, I can look for what's familiar and go, well, I know all of my Y values are going to be positive, right? And so I already get a sense of something is going to happen here. Now, if you really wanted to dig deeper with your students, you could ask another question. If I have a number greater than 1, like 2 or 3 or 749, and I square it, is my result bigger or smaller than the number I'm squaring?
Normally bigger.
Right, bigger.
In
right?
naturals, it will be. Right?
Well, even in, if I had 743 times the square root of 2, if I square it, if it's bigger than 1.
If it's bigger than 1.
Right, if it's bigger than 1. That's
Yep.
what I'm,
Right?
yeah,
Yep.
if it's bigger than 1.
If it's smaller than 1, if it's somewhere between -1 and 1, right? So 1/2. If I was to square 1/2, does it get bigger or smaller?
Smaller.
Smaller, right? So when I square numbers between 0 and 1, they actually get smaller. So that's a curiosity, right? So without even thinking of what this picture looks like, just looking at the symbols, I can start saying, well, I know that between -1 and 1, if I square it, I'm going to get something smaller. At 1, I get itself, and more bigger than 1 or less than -1, I'm going to get bigger numbers, and they're all going to be positive. So I can sort of start thinking just from the symbols and what I know about things being squared, what happens.
Hey, Gianna, it sounds like, okay, she muted it. That was the beautiful piano music.
So then let's look at numbers, right? So our students may not be ready to have that symbolic conversation, right? Our older students may, our younger students may not, but we can use numbers, right, to do what we just did. And numbers kind of feel familiar. So I started off our table here, and I can have a table with as many values as it takes, right, to see patterns. But I said, okay, if I put 0 in, I know I'm going to get 0. When I put, let me make sure I put this on, all right, -1 squared is 1. What's 2 squared? 4. What's -pi squared? I mean, what's -pi?
Squared.
It's going to be pi squared. And I included that one because I thought that it, not cubed, squared. Because I wanted to take a minute to talk about the fact that what would make that ugly would be if we used a decimal approximation. And I asked you to go ahead and multiply that all out. And then you're stuck going, okay, well, how much? 3.142, I think, is what the math map uses. Now that becomes really a lot of cumbersome calculation, right? So in the math map, we really encourage students to use the exact form of the number, right? Which means that the right answer there is pi squared. which is a lot easier than multiplying out the decimal approximation. Okay. I always say, if you're buying carpet, you have to use the decimal approximation, right? If you're doing something like that. But I just wanted to point that out, that in the math map, we're really encouraging students to leave exact answers. So they're going to become familiar with using, those symbols, right? Which eventually can become X's and Y's and whatever other letters we use. But we're going to build that familiarity by talking about numbers that have an exact form. And then we talked about this. What's 1/2 squared? Who remembers?
25.
1/4 or 0.25. I love fractions. My kids don't. So for my younger students, I can start building a table. For my older students, I can always build a table. For myself, I can always build a table. So if I see a function and I don't know what this looks like, I have this limitless supply. It's really amazing. It's really cool. God gave us as many numbers as we want to use. Right? So it's kind of like, he has cattle on 1,000 hills. He has given you an infinite number of numbers that you can use to look for patterns. So I don't know what this looks like. I'm just going to keep putting numbers in and seeing what the result is, right? Maybe what's -5? Oh, I get the same answer, right? I can use numbers to look for those patterns. And then I can come over here and look at my image. Now, one thing I could do, right, is look at my 0, 0 and say, well, I'm going to plot that point. There you go, 0, 0. I could plot -1, 1. I could plot 2, 4, right? I could plot -pi and pi squared, which is going to be somewhere up here. Right?
About 10, right?
Yep. And then I could plot my 0.5 and my 0.2, right? And so as I start putting my points, right, I start to get a sense of what this shape is going to look like. But I could have started with the picture too, right? Maybe from your grammar, you remember that x squared looks like this. And I could come over and say, okay, well, here's 1, 1, and here's my -1, 1. Oh, and look, outside of those two numbers, it gets big faster, right? My numbers get bigger. But in between, there's this, it's slowing down somehow, right? The change is slowing down. That's what we talked about when we talked about, right? What does the squaring do? So we talked about when we looked at numbers. And so notice how I can take my symbols, my algebra, I can use numbers that feel a lot more familiar, and I can use geometry, what the picture looks like, to teach me something, a cohesive whole about x squared, right? Which is something different to, right, whatever I may have known in the past, right? By putting all of those pieces together. So a lot of curricula are going to teach these separately or maybe all together quickly. And one of the things we're really trying to do is integrate these ideas. So we've looked in week 7, we looked at what powers were, right? What does that look like? Now we're saying what happens when I use a power in a function. We're going to look at other things we can do with it later on, right? And looking at these powers, but looking at it from an algebraic, arithmetic, and a geometric perspective is going to help us to understand.
Something I want to remind you guys is that this is why we play Natural Number Knockout or Board Slam, whatever you call it, in the Essentials program. This idea of being able to square and use powers, really a lot of facility, will help algebra just be a lot easier for your students.
All right. Okay. Anybody have any comments on this before I flip to the next?
I just wanted to ask a clarifying question on the chart.
Mm-hmm.
So we're on the column where it has parent and general equations. So the y = 0, y = x to the first, y = x. That's the parent equation?
Yes.
Okay. And then the general equations are the ones that on the bottom?
Yeah.
Okay.
Can you see why it's the general equation? If we would replace the 0, 1, 2, and 3 in those general equations, that indice, with the letter N, meaning any index, then that equation is the equation that you use to draw any kind of shape that you want, any kind of function.
That went over my head. Sorry.
You want to try again with the pointer there, Kirsty? Because I can't point.
Okay, sorry. Say that again. I got distracted by the chat box.
If you look at the ax minus 3h to the 3,
yep,
and then the 2 and the 1 and the 0. If you wrote the letter N there, meaning any number could be there.
If you wrote N where?
Where the 3 is, or where the 2 is, or where the 1 is.
Okay, gotcha.
Or the 0.
Oh, yeah. Okay.
Do you see how it's the exact same equation and all we did was change the index?
Right. Okay.
So this is why it's the general equation. That equation tells you everything about every function that there is in the power functions. And then what your job to do is to put one little piece of information in each equation until you understand it better and better.
Okay. And then that slope intercept form on the line, is that just extra, or what is that?
It is extra just because we're all so familiar with that we wanted, right? If we just gave you this and right, people would be like, what's that? That's not the right. So since 2 weeks ago, we really talked about slope intercept form. We wanted to include that just so that people could see these are all different ways of writing the same equation of a line, depending on the information that we're given.
Okay, but that's not apparent or general.
It's a bonus.
Yeah.
So that's the thing that's hard with math. I mean, that where Kirsty and I go back and forth a lot. Y equals mx plus b is a very common form, and it's super helpful, and it tells you so much about a line.
Right.
But people never make the connection that the line could have been a curve in one of these other functions.
Right.
Because they only see y equals mx plus b. So let's look at it. Let's take the moment to do that. What if your n, or your number is already 1 there in your index? What if your k was 0 and your h was 0? Then you'd have y equals a times x to the first, right? Well, you can drop the 1, and now you have ax. You don't need to write the 1. Well, what if a is also equal to, what if we said a was equal to m? Now you have your y equals mx. So if you play around with different with different numbers in those variables, you'll see that you can actually come up with y equals mx plus b from the general formula.
Mm-hmm.
So to me, in many ways, it's a cheat. It doesn't help the person who can really understand math understand it. On the other hand, it's y equals mx plus b is a super helpful equation. So since it's so commonly used, we threw it in there. If it causes confusion, we could do it as a footnote. Yes, everyone. Go ahead, Kirsty, explain what you did.
So I just multiplied that out, right? So I said, okay, if I multiply this out, since this is a 1, it's the same as x minus h. So I can distribute my a, and I end up with ax plus ah. And then since those are just numbers, I can take my a, h, and k, and they're going to equal my b, right? And then my m is my a. That's my slope. Because what's happening, let's see. Well, I'll just squeeze it in here, right? What's happening is here's my line, and let's say that my slope is 1, right? So this is my line where my slope is 1. Well, what I'm saying is if I was to shift it, h tells me to shift things left and right. If I move that left, and my k tells me to move it up and down, and I move that point up, right? Then what's going to happen is that may change where I cross, right? So I'm taking that point and I'm moving it up and down, and my slope is going to impact that. So I end up with this sort of formula there where I can either talk about how my line has been shifted left, right, up and down from the origin. But if I put all that together, it's going to give me my new intercept. So
So does the H and the K and the line kind of correspond to like the H and the K, how it gives you your vertex on your parabola?
Absolutely. It's the same thing. So that's all that H and K means is, right. So if we come over here, let me pick a color that like white. Right. If we came over here and I have my axes, H is no matter what kind of a graph that I have, right? So it could be my parabola, it could be my line, it could be the sine function. My H tells me to go left or right. My K tells me to go up or down. And what it says is every single point, right? Move it to here, right? And so now my parabola would be centered, would have its vertex there. But if it was my, right, if it was my cubics would move. That's all H and K are telling me. And it's true for everything. So where you've learned that and said, okay, I remember this was true for the vertex of a parabola, we're telling you, no, this is true for all of these functions, right?
Okay.
So we're going to broaden that and we're going to say this is true for all functions. So if you know what that function looks like at the origin, I can move it around using that H and K. Does that help?
Yeah, it does. I've never seen that before. That's really cool.
Math is really cool. There's like all these patterns, but we've lost so much of it because of the way we teach it. And so by grouping things together and we're constantly looking for what's the pattern here, we're going, oh, this is really, really neat. That we've lost so much that we're trying to bring back in the math map. So
thank you.
Okay. I am going to give Lee an opportunity to talk about our sponsor.
So thanks to Classical Conversations, our classical Christian community, where folks who are members can go to ccconnected.com and download the beta version, which means it's free, of the naturals, so that parents can go ahead and practice all the notations that kindergartner would need in order to do well in college. How's that for a promise?
I think it's a pretty good one. Okay, so one of the things I really want to say is that most of us have some recollection of these concepts or topics from our own high school education or even our college education. And we're going to be tempted to look at these charts and go, oh, we have to understand it all. And that's really tempting. And it's like that first year of essentials where you're like, I got to get it all. And then the second year you go, oh, I can rest. I don't have to get it all. It's the same thing with the math map. That these ideas that Carrie's like, oh, I'm really wrestling with this, right, is a big idea, and it's not a grammatical idea, right? So the grammar, that was not really grammatical. We can make it grammatical, and in lesson 18, we'll talk about how we can see it as grammatical. But I want to encourage you that if you're looking at some of this and you're feeling like you should understand it, to let go of that and say, I don't. Let's first look at this grammatically, and what's the grammar that I can learn? Because your students, right, for most students, when they come into this is not something they'll ever have seen before. It's going to be new, and we want to be able to step back and say, no, this is just a grammar exercise. Memorize these formulas and the graph that goes with it, right? We're not trying to understand this the first year. And we've talked a little bit about the domains and how that works. These images, right, and these formulas are in the naturals lessons. So if you haven't downloaded those naturals lessons, go get them, right? Especially for this week, because all it is saying, look, just learn the picture. And so imagine if you're now a challenge A, challenge B, challenge 1 student, right? And you're coming into this a few years from now, you may have been doing this for 6-7 years, right? And you're like, I know that's an x squared. I know that's a parabola. And we're going to say, well, now do something with it, right? So I just want to encourage you, if you're thinking, oh, this is way too much, right? It's just the grammar, and it's not a 1-year grammar program, right? This is a 13-year grammar program, right? 13 years to get this. So if you didn't understand what the questions that Carrie was asking, that's okay, because we don't expect you to. But one of the things that I do want to talk about when it comes to grammar that we want to look at is the grammar of curves, right? And that's, how do we talk about these curves? So I have created some lines and curves that we can talk about using these words that are up here, right? So let's look at things like increasing, maximum, decreasing, minimum, right? And let's just use those 4 words tonight: increasing, maximum, decreasing, and minimum. And let's look at our curve here. And if we matched it up, we could see, all right, we're talking about our constant over here. And Lee already kind of gave us a little hint as to why it's called the constant, right? So is this function increasing or decreasing? Does it have a maximum? Does it have a minimum?
No.
No.
None of the above.
None of the above, right? And so we don't need, so we can look at this and we just say it's constant. That's why. So let's look at the next one. And we're over here now looking at, right, our line. And again, using increasing and decreasing. When we talk about increasing and decreasing, we're always going to talk about going left to right. So just like we read and write letters, we're going to look at graphs from left to right. So would anybody like to hazard a guess? Is this an increasing or decreasing function?
Increasing.
Increasing, right? It's getting bigger, it's going up, so it's increasing. Are there any maximums or minimums?
No.
Nope. All right, how about this one? We just looked at this one. What's it doing to the left of the origin?
Decreasing.
Decreasing.
Decreasing. And to the right of the origin?
Increasing.
Increasing. And what's happening right at the origin?
The
That's the
minimum.
minimum.
There's my minimum. All right. So notice we're just using words, but now if I closed my eyes and you told me, right, what you were seeing, I could get a picture because we know what the words mean. So here's x cubed. Anybody want to describe that?
Increasing.
It's always increasing, but it's different to our line, isn't it?
Yes.
Right.
But
And
you
so
wouldn't know that from the words we've been using.
we
Right.
wouldn't, right?
I
But
don't
it's
think-
it's increasing. So guess what? If I know it's always increasing, I know that at some point it has one end down here in this quadrant, and it has another end up here in this quadrant. Right. Whatever happens in between, my ending behavior, right, is in those same quadrants. Right. So even though
So
it's funky stuff in the middle.
I was going to say, so it's beyond the vocabulary we were just given. Is there anything else on that line of vocabulary that we could use in this? Like, it doesn't really look, it's not really concave because
Nope.
it doesn't really have a full curve there. Is there a word for that middle section?
There you go. I just circled the 3 words we could use, right?
It's the
So we
point
could-
of inflection.
So we could say it is increasing, right? But it's decreasingly increasing, right? It's not increasing as fast. And then it becomes increasingly increasing. It's increasing faster. And in between, where it went from decreasingly increasing to increasingly increasing, there's a point of inflection.
So is the point of inflection almost a symmetry point?
A local, in this case, yes. Not always, but it always may be a local point of symmetry. The point of inflection is where my concavity changes, right? So here's my concavity words. So I could say it's concave down here, and then it's concave up here, right? So there are more words. I just was trying to keep it simple for tonight, right? But you can see here on this piece of the chart, right? We've got all of these different words that we could use to give a description of what's happening. All right, I'm going to clear these. Well, I thought I was going to clear them. It doesn't want to clear. But, well, I don't know how to make it clear since it doesn't want to do that.
Kirsty, it's probably because we're out of time.
Oh, sorry. Well, I have more, but we'll just have to save for next year. Because this is so much fun. But hopefully you see that this is it's not going to be hard, right? Because we're going to take it and we're going to look at the grammar. And grammar is only unfamiliar or familiar. It's never hard.
Good words to end with. All right. Thank you guys for hanging out with us week after week. I'm having a great time and it's really good to see your faces. So see you next week.